Today we'll be tackling a very important definition, or a couple very important definitions in chemical engineering thermodynamics. And these definitions are for the bubble point, and the dew point, the dew point. Now, when we talk about vapor-liquid equilibrium, which is where the bubble point and dew point come into play, we talk about a graph that looks something like this, and I'll just draw this out, where we have a pressure on the y-axis. This could be temperature or pressure depending on what you're holding constant and what you are changing in your system, but for right now I'll just use pressure to demonstrate an example. And over here is our liquid and vapor mole fractions. Our vapor liquid equilibrium graph might look something like this, where anything above this red line is called the liquid line. So let's just say liquid. This blue line will be the vapor line. So anything above this liquid line at the higher pressures is going to be, of course, our liquid. And anything at these lower pressures is going to be our vapor. And everything in between is our vapor-liquid equilibrium. So the bubble point. The bubble point is defined as such. And let's just define a quick exemplar system. Let's say that we have some chamber here in which we were able to adjust the pressure. And if we had, say, a completely liquid system and we decrease the pressure of this system. So right now this is under a higher pressure that is forcing the system to be in a liquid phase. As we decrease the pressure, so let's say we have some piston. Let's say we have a piston up here. Something like this. As we move this piston up to relieve the pressure on the system, we will actually be forcing some of the liquid in this system to go into the vapor phase. That's how the reduction in the pressure of this system will actually force some of this liquid to go into the vapor phase. And that can be demonstrated here. So if we were starting at some initial point, let's say right about here, this is our initial starting state, at a higher pressure where we have an entirely liquid system, as we go down and meet our liquid line and start crossing into our vapor-liquid equilibrium, we will have the first bubble of vapor forming in our system. And that is the bubble point. So in this case, we'll be holding temperature constant since we're looking at a pressure versus mole fraction graph. So T is constant. So in this case, it is the pressure at a constant temperature at which the first bubble of vapor forms. That is the definition of the bubble point. The dew point works sort of in a reverse fashion. So say we have some fully vapor system. So we're starting down here now. I'll keep this white. So this is our initial stage. At this constant temperature, as we raise the pressure and we meet this vapor line here, and we start crossing into vapor-liquid equilibrium from the other way, we will see our first dew, or our first droplet of liquid forming in our system as we raise the pressure and cross into vapor-liquid equilibrium. And of course, you can definitely replace this P with temperature and replace this temperature with pressure. So we're saying we are at a constant pressure and we are changing our temperature. In that case, we will have our vapor forming at the higher temperatures at constant pressure, and our liquid will be forming at the lower temperatures at a constant pressure. So that's just a little look into how our vapor-liquid equilibrium works and how we are able to use something called Raoult's law. So let's define Raoult's law. Raoult's law. Now, Raoult's law deals with ideal conditions. And what we mean by that is that if we had some ideal binary mixture, Raoult's law would apply and give us the partial pressures, the saturation pressures, as well as the overall pressures based on the liquid and vapor mole fractions, not concentrations, mole fractions. So Raoult's law is defined as such. It is defined as the liquid mole fraction of component I times the saturation vapor pressure of, or rather just the saturation pressure of that component is equal to the vapor mole fraction of component I times the total pressure. This is Raoult's law. So let's start with deriving Raoult's law for our bubble pressure. That will be the first thing we'll look at here. So put our bubble pressure. The way we are able to calculate our bubble pressure, remember the conditions for bubble pressure is that we have a constant temperature, and it is the pressure at which the first bubble of vapor forms. So first vapor bubble forms. And the way we manipulate Raoult's law to give us this. So let's rewrite it. I'll rewrite it in this way. So now we have our components, our vapor mole fraction of component I, and we want to find the bubble pressure. So I'll write this here, equal to XI PI sat. And what we'll do to derive this is we'll take the summation of both sides. And what ends up happening is that we know that if we were to sum up all the mole fractions in the vapor phase, well, simply that becomes 1. If we take the summation of all the vapor mole fractions, every mole fraction in the vapor phase, that should equal 1. That's Dalton's law. So because of that, we set this equal to 1, and what we are left with is that the bubble pressure is equal to the summation of I components times its saturation pressure at temperature T. Which is something that we should be defining before we find the bubble temperature, or the bubble pressure. Since it is at a constant temperature, we will find the mole fraction of that component in the liquid phase, multiply it by its saturation pressure at temperature T, which will give us our bubble pressure. So this is our first derivation using Raoult's law. Now, the next thing that we can derive, the next easiest thing probably I would say, is our dew pressure. So P dew. And now we are kind of reversing the situation. Now we have a constant temperature still. And now this is the first, let's say liquid drop formed. So remember that in this situation where we're looking for our bubble pressure, we initially started with a system that was a fully liquid system. We were then decreasing the pressure to allow some of that liquid to coerce itself to go into the vapor phase. With the dew point, it's the opposite. Now we have a fully vapor system and we are increasing the pressure. We are lowering that piston, airtight piston on that system to coerce the liquid to start forming. So that's why in this case we are working with the liquid mole fractions, because we have an entirely liquid system and we know the compositions of, or theoretically we will know the composition of the system when it's liquid. In this case, we do not have the liquid mole fractions, we have the vapor mole fractions. So let me rewrite. So now we are looking at finding the dew pressures, right? Is equal to XI PI saturation. Now we don't know what our liquid mole fractions are. So what we'll end up doing is we'll send our saturation pressure over to the other side. Send this to the other side. So divide by PI saturation equals the liquid mole fractions. And again, we'll take the summation of both sides. Let me draw this out a little better. And like last time, the sum of our liquid mole fractions has to be equal to 1. So we kind of ignore the fact that we even have this term in our final equation. And now what we can do is we will force the dew pressure onto the other side. So what we have in the end is our dew pressure is equal to 1 over the summation of the vapor mole fractions over the pure component saturated pressure of component I. So this will give us our dew pressure. Now, calculating our bubble temperature is going to be a little bit different. It kind of won't be this nice and easy equation. In fact, we'll have to do a little bit of solving backwards almost. So let's toss number 3. Number 3 is going to be our bubble temperature. Now we are reversing the fact that we had a constant temperature, because now we are adjusting the temperature to meet our bubble point. So we'll instead have a constant pressure this time. And it's the same conditions for the bubble pressure, which was the first vapor bubble forms. We know that. So let's kind of use, or I guess, yeah, let's kind of use this as a starting point. So we know that as part of this equation that we have, or actually, you know what, we'll just write this out from the beginning, right? So YIP, which is the total pressure of the system, is equal to XI PI sat. And once again, we don't know our vapor phase compositions because we have a completely liquid system. So we'll divide over the pressure to this side actually. So YI equals XI PI sat over the total pressure. Again, we'll take the summation of both sides. Again, this is equal to 1. So what we have is 1 equals the summation XI PI sat, which is a function of temperature over pressure. Now this temperature this time around isn't just a constant temperature set by our system. This is now our bubble temperature. Well, now we run into an issue. We look at this and we say, well, okay, this is all fine and dandy, but now our bubble temperature is nested as a function of our saturation vapor pressure, or saturation pressure of the pure component I, rather. How are we supposed to even calculate this? Well, the answer is that we don't really even calculate it. What happens is that if we rewrite this to where we take this total pressure multiplied on both sides, subtracted over, we have 0 is equal to this summation PI sat bubble temperature, and this will be minus P. As long as we select the correct value for our bubble temperature here, this equation should hold true. In a sense, this is our bubble pressure, or rather, this is the pressure of the system. Kind of can think about it as a bubble pressure, but that's a different, it's not necessarily what's going on here, because we could have, if it's a constant pressure, as long as you meet that temperature requirement, that does become your bubble your bubble pressure as well. Essentially what ends up happening is that you need to use iteration to find the value for this bubble temperature that makes this equation hold true. I don't like that. So as long as we find this bubble temperature that satisfies this equation, that is the bubble temperature for that specific pressure. Now the last thing that we're going to derive here is, of course, our due temperature. Now this one is the same thing. We have a constant pressure, same conditions for the due pressure, which is where it's the first it's the pressure at which the first liquid drop is formed. This is now going to be the temperature at which the first liquid drop is formed. And the way that we get there is kind of similar to how we got here. Well, let's start back up with our Raoult's law. P equals XI saturation. Now at this point we don't know what this is. Our X, we don't know those because we have a fully vapor system. So we'll end up dividing both sides by the saturation pressure. So YIP over PI saturation, which is a function of temperature. And this will end up being our due temperature is equal to the sum of x's, which is equal to 1. So again, it's kind of going to be this other iteration that we have where as long as we have satisfied this equation here, then we should have what our temperature, what our due temperature at the given pressure should be. So now we're in a brand new Python notebook. As you can see, I've installed a whole bunch of libraries so that we can work with these as we go along. But most importantly, I want to use this props thing, and this props is short for properties. And I'll show you what that does. So our problem statement defines that we have a 40-60 mixture of benzene and toluene. This is our binary system that we're going to be dealing with to find our bubble pressures and temperatures and whatnot. So I'll show you. So if we pull from this props library our two components, benzene and toluene. We'll start with benzene first because benzene is the more volatile of the two than toluene. So this is essentially going to pull a table of properties, including the saturation vapor pressures that we need to continue on with this problem. Or saturation pressures in general, not necessarily the vapor pressures. So if we pull this, it's going to pull this item at some designated location that's already defined in this Chem5 library. So I'm going to set this just as P. So if we ever want to reference, well, I want to know what the vapor pressures at a given temperature are. So this is a function of temperature. Say at 350 Kelvin, it returns us an array that is coincidental with the order that we put our two components. So this is the vapor pressure for benzene at 350 Kelvin. This is the vapor pressure for toluene at 350 Kelvin. And you get the idea. So now let's start defining our function. So our first one will define our bubble pressure, bubble P. You need to give it inputs of the liquid phase, mole fractions, and temperature, because we want to analyze this for a certain temperature. Well, you might be saying, hold on. We don't know what our compositions are yet. So let's define that. So we said earlier that our problem statement calls for, and I'll put this in an array, calls for a 40% mole fraction of benzene and a 60% mole fraction of toluene. So now we should be able to create this array to use later on. And the next thing we're going to do is we're going to code out our bubble pressure equation that we had derived earlier. So we know that the bubble pressure is equal to the sum of the liquid phase mole fraction of component I times its saturation pressure at temperature T. So let's just say like this is the bubble pressure of component I if it were just a single component, and we'll sum this later. So this is equal to our X times our saturation pressure at the given temperature. So P dot P vat at T. And we want our final sum, so P is gonna equal our sum of the array, right? And we want to return, of course we want to return the bubble pressure, but we also want to return the liquid phase mole fractions, which we can easily get by dividing the bubble pressure by our saturation pressures. So we'll go something like Pi over P. I want to take a quick second and make it a little bit more clear by what I meant. So when we do this bubble calculation here, we already know what our liquid phase mole fractions are. That's an input of our function. So what we want to output is actually our vapor phase mole fractions here. And if we want to get our vapor phase mole fractions, well, that's simply dividing this side over here by our bubble pressure. And if you remember in our Python code, right around here, we define Pi as our vapor phase or liquid phase mole fraction times our saturation pressure at the given temperature. And so that's exactly what we're doing here. This Pi is our xi P sat divided by our P, which is our overall bubble pressure. So now if we were to call our function at, let's say we want to analyze it for 350 Kelvin. So the first thing that I should have probably done is I need to define this as an array. Otherwise it won't do the math properly here. It's going to try and use a dimensional argument to kind of push out an error that we don't want. And we also, of course, need to give it the composition that we have. So that is in array Z. So now that we do it, boom, we now have our bubble pressure of our binary system as well as our mole fractions for each of our components. So this first one is benzene, as is in our convention, and the second one is for toluene. So it always follows this order of volatility that we had initially pulled our properties from. So now let's do the dew pressure. Right, so we're going to define a new function, and this is going to be the dew pressure, dew P. And this time we're going to have inputs of our vapor phase mole fractions, because remember we have an entirely vapor system at some temperature. And if we go back to our whiteboard down here, our dew pressure is equal to the sum of Y over the saturation pressure for the given component. So let's throw these in. So we'll call up our pressure, and this is going to be equal to our P dot P vat at our given temperature, and our dew pressure that we are wanting is going to be equal to the sum of 1 over the Y value that we provided over the Pi. Just double check that we did that correct. Yep, 1 over sum of all that. Maybe I should do it like this. Over this, just to make sure that we're doing the right thing. And now what we want to return is, of course, our dew pressure. And we also want to return the vapor phase mole fractions that we can grab. Or sorry, we want to return the liquid phase mole fractions. And we will get that by multiplying our y's by our dew pressure, dividing it by our pi sat. So it'll look something like y divided by pi, or no, y times pressure, our dew pressure divided by our pi. Cool. So now let's see. We'll do a dew point calculation. Dew p. And we'll do it for the same vapor phase. Now our composition is going to be for our entire vapor phase. And our temperature, we'll keep it at 350. And now we see that our dew pressure is this number here. And our mole fraction for benzene. And that's our mole fraction for toluene for this composition at this given temperature. So now that we have the pressures out of the way, let's move on to doing the temperatures. So get this out of here. Now we'll define a new function for our bubble T, and this is going to have inputs of our liquid mole fractions as well as our pressures, our pressure of the system, the constant pressure that we have our system at, basically. Right? So how do we define this? Since we are kind of doing the inverse of this function earlier, one way to do it is to start defining another function. We'll call it like the target function. So target func, something like that, where we have inputs of temperature. And this function is actually going to be this bubble P over here. So we'll say like this, we want to return bubble pressure, so bubble P, and this has inputs of our composition and T. Remember though, when we have our outputs, our first output is this pressure, that's our bubble pressure, and the second output is our mole fractions in the vapor phase. We don't want to use this in our calculation because we only want the pressure, and that's what our target is. We want to set the pressures equal to each other as we did here. So this is our pressure at the bubble temperature, which would end up being our bubble pressure, and this is the target pressure, which is the pressure of our system that we're holding constant. So we don't want the mole fractions, we just want to have this target pressure. And so in order to pull that value only out of this function, we use a bracket 0, and that will pull the first value, which is the pressure. From that, we will subtract this pressure that we supply as an input, and if this should return 0 if we are given the proper temperature. But instead of doing it this way, where we have nested functions and it kind of just looks a little bit more complicated, another way that we do this is we use something called the SciPy optimize library. And the specific function we're going to be using is called Raoult scalar. Now, to be clear, we would have to use this in the other situation as well, but this way that we're doing it now is going to get rid of that nested function, that target function. Instead, we can define it as an anonymous lambda t. And this is basically saying, well, I'm going to define some anonymous function. It's a one-time use thing as part of this optimized Raoult scalar that has an input of t, and it kind of sings the same song. So now we're going to use our bubble pressure. Oh my lord. Our bubble pressure with inputs of the liquid phase mole fractions and the temperature minus P. This is our target function with the addition of having our bracket 0 here to pull just our bubble pressure out once you do that calculation. This here is our target function. Our function to 0 is defined right here. Now, the other thing that we need to give it is we need to give it an initial guess. Now, initial guesses are very important because this is a good initial guess will give you a more accurate result in the end. But right now, we don't really have a way of getting that initial guess. So we'll just throw some random number, let's say 300 kelvins in there. There are ways to grab this initial guess that might be a better initial guess than just a random 300 kelvins, but we won't get into that right now. We'll select the method. We'll select the Newton method. And we want to pull the root of this function to use as our temperature. Okay. Now we want to return, of course, the temperature. And we also want to return the vapor phase mole fraction of that first bubble. And we do that by having our liquid phase mole fractions times the saturation pressure at the given temperature over the pressure. So we code that out like this. So our yi is equal to x times the saturation pressure at the given temperature over our bubble pressure. Right. I think that should be good to go. So now let's make sure that this function works. So first what I'm going to do is I'm going to use our bubble p function. We're going to have our liquid phase mole fraction, which was defined in Z, and we'll set it at 350 kelvins. And we get this pressure value right here for our bubble pressure. So I'm just going to copy that. And now if we throw it back into our bubble temperature, which is technically an inverse of the bubble pressure function, throwing this pressure value back into the bubble temperature function should give us 350 Kelvin. This is how we can check to make sure that our bubble temperature function was coded correctly. So we're going to go bubble pressure or temperature here. And it'll have inputs of course, our liquid phase mole fractions and our bubble pressure that we had just calculated. If it's done correctly, bingo, we have 350 kelvins, and we also have our vapor phase mole fractions of that first bubble that forms as we decrease the pressure of our all liquid phase system. Now the last thing we're going to code out is our due temperature function. So I'm going to get rid of these cells again. I'm going to define a new function, the due temperature function. And it's going to look really similar to actually our bubble temperature function. So what I'm going to end up doing is I'm just going to copy this over, paste it here, and we're going to do the same thing. We have an anonymous function, and this time it's going to get an input of pressure. And let's see, or no. This still stays as temperature. We're still doing temperature calculations, of course. But this will change to the due pressure instead of the due temperature. All right. So now we have an input of our vapor phase mole fractions matching up right there. We still have an initial temperature guess, which is a dumb guess, not necessarily based on anything in particular. And this time our return for our our liquid phase mole fractions is going to look like y times p over p dot p vap of t. All right, and that makes sense. That's how we have it here. So this should be all right. Just do a quick double check here. Yep, everything looks good. So let's shift enter, and we'll check it in the same way we checked our bubble temperature calculation. So we'll do a due p of z and 350 Kelvin. We have an output for our due pressure, Control C, and now our due temperature, due T, input to Z and our pressure. should give us back our 350 Kelvin, and we now have our vapor phase mole fraction. So that is all 4 of our bubble point and dew point calculations coded out. And now the next step is to plot these out on pressure versus mole fraction, temperature versus mole fraction, and then vapor phase versus liquid phase mole fraction graph. So first, let's plot out our x's that we're going to use. And more specifically, I'm going to call these my x1s. These are the liquid phase mole fractions of my more volatile component, which is benzene, according to our nomenclature scheme here. So I'm going to make this a set of evenly spaced data points from 0 to 1, because that's the minimum amount you could have in a system and the most amount you can have in a system in terms of your mole fraction. So I'm going to go something like NP lin space from 0 to 1, and let's say I want 20, maybe 20 evenly spaced. Why did it do that? All right, so I have my x1s now, and I'm also going to define that we're at a constant temperature, because if we're doing our if we're doing a pressure versus xy graph, you need to hold it at a constant temperature. So we're going to have this equal to 350 Kelvin. Why not? Now, the next thing that I want to do is I want to create a for loop. And why do I want to create a for loop? Well, we're going to keep doing our bubble temperature calculation over and over and over and over again, so that we can get our set of plots according to our x1s. So I'm going to say something like for x in, and remember that this needs an input of an array of 2 values that are according to our benzene and toluene compositions in this case in the liquid phase. So I'm going to do something like np dot column concatenate our x1s and our 1 minus x1s, or technically this is our x2s. Oh, I should probably, yeah, include input, but I just want to show you what that does. So we're going to have, oh my goodness. So I'll show you what this does. So now we just have basically a set of liquid phase mole fractions that we can use to plot out our data. That's essentially all that's really doing. Now we need to set up 2 arrays, and I'm going to make these empty arrays for our p's and our y1s, because remember, these are the outputs that we get when we do our bubble pressure calculations, our p and our vapor phase mole fractions. So we're going to store them in here, and essentially we're going to be doing, so bubble p inputs x and t, which we have our x is being taken from our array, our t is a constant value for that, and we want to pull our pressures. So p's dot append, and that's going to be our value from our bubble point, x and t. Well, first, actually, you know what? Just to make this easier, I'm going to unpack this into our pressure and our y's. And in our p's, we're going to append, of course, our pressures. And for our y's, we're going to append our y's. Okay. So when we do this for loop now, let's take a look at our p, or yeah, we'll look at our p's. Why not? P's. All right. So we have 20 values, or 20 or 21 values of just pressure plots that we have based off our bubble point pressure calculation. And we notice that each of these bubble point calculations is its own array. But if we want to be able to plot this out, we want it to all be in a list in one array. So one way we can do that is we can do an np dot, or we'll redefine our p's. So np dot row concatenation of our p's array, and we'll do the same thing for our y1s. Y1. I just think we need to take these parentheses away. Yeah, now it's happy. So now that when we get our p's, we have a nice list that we can just straight plot for our bubble point plot. Okay? So now let's start doing our plotting. So fig equals make subplots. Right. And then we're going to add scatters. Add scatter. Fig.add scatter. Our x's, we'll do our bubble curve first. Our x's is going to be equal to our x1s. Our y is going to be equal to our p's. Our name, we're going to name this our bubble. Method will be lines. Or not the method, our marker. Mode equals lines. And there we go. This is our bubble point curve. We'll do the same thing for our dew points here. So our dew are going to follow our y's. So a little small mistake that we made here. Remember when we were talking about we only are worried about our benzene for this curve? That means that we're only looking at that first column of y1s. We're not worried about the y2s that happen in the second part of that array. So if we look at this now, this is just the list of the vapor phase mole fractions of benzene in our system. So now we have a nice curve for our dew point and a nice curve for our bubble point. I'm just gonna make this look a little bit nicer. So update layout. We'll go with 800, equals 600. We'll add a title. We'll call this benzene toluene VLE at T equals, and what we're going to do here, we're going to make a callable out of our temperature here by using these squiggly brackets. And this means that every time that we update our temperature, every time we look at a new plot for a different constant temperature, it will automatically update in our title here. So that's nice. We'll have an x-axis title. We'll make this x comma y. These are our vapor phase and liquid phase mole fractions. Our y-axis will be our pressure. So P in pascals. And there we go. We have a nice vapor liquid equilibrium graph for our benzene toluene system at temperature equals 350 Kelvin based on our pressures and our mole fractions in each phase. Now next we want to do our constant pressure temperature versus mole fraction graph. And I think the easiest way to do that is I'll set a pressure up here, So this will be equal to atmospheric pressure, 101,325 pascals, like that. And I'll open up a new array for our T's. And I'll do another calculation here for our T and our Y's based off our bubble temperature calculation. Bubble temperature that has inputs of our compositions and our pressure. And we'll do a T's append for every T that we have. And same thing down here. np.row concatenate of our array of T's. As long as that looks okay, we can add a new scatter here now. We'll add rows and columns. So we're gonna add one row. We'll make 3 columns because we'll do a third one for just our X versus our Y. So we'll do 3. We'll assign this to row 1, column 1. Same as this one. So actually, I don't know about having all these on the same graph. I'm gonna just leave this one as is. And make a new subplot down here. So let me just copy paste this. I don't think I need this here. Get rid of this. Get rid of this. So now X is equal to our X1s, our Y is equal to our T's at this point. We can keep that, it's not going to affect anything. Change this to our T's as well. At pressure equals P pascals. And our Y is going to be our T in Kelvin. So let's see if that, oh boy. Here, I don't think this is interfering with each other, so I'm just going to get rid of this. Here, I'll copy this. No, don't want that. P equals 101,325 pascals. Our T's and our Y's are set up. So for now, X in our range of liquid phase compositions, bubble T, inputs of X and P. So this is going to be our temperature and our Y. So our T's append. Make sure everything here is following your temperature. Make sure that looks fine. This axis doesn't look right, and that's because I missed a couple things here. For one, we want to append temperatures to this, and we want to append that. Make sure that we're concatenating the right thing. Oh boy. And now it looks like we have a nice now the last thing that we want to plot out, and maybe I'll just plot it right next to here, equals 1 equals 2. One last thing that we want to code out here is our X versus Y graph. Add scatter. So now we have our x is equal to our x1s, y is equal to our y1s. Name this, I don't know, like our xy, something like that. Just see what that looks like. We'll assign its column, assign its column 2. Oh no. Assign that to column 1, and then assign this to column 2. Right. See, now we have two separate graphs. This is our XY relationship. One thing we might want to throw on here is a 45-degree line that shows the deviation of our XY ratio from a perfect 50-50 ratio. Fig dot center. And here we're just going to have our x is equal from 0 to 1, or y is equal from 0 to 1 as well. So this is going to match up. We have 0.00 and 0.11. So if we throw that on there and make sure that we designate it properly. Set this mode equal to lines. So now we have a temperature versus mole fraction graph. We have our mole ratios, and we've also plotted this trace that lets us know how much is deviating from just a perfect 50-50. And we have this pressure versus mole fraction graph to find our bubble points, our dew points, same thing here. And this is to analyze our mole fraction ratios.